Lesson 10.10, Taylor and Maclaurin series. We're going to start this section by integrating a Taylor series and find a new series from it. We ended our last section by differentiating a Taylor series. So this part we're going to start by integrating a Taylor series. So one thing we want to remember is we can do it term by term, because if we're asked to find like a fourth degree Taylor series or like a third degree Maclaurin, we can just write out the terms and integrate them term by term. Or we can do it from the summation form. So we want to remember that it's the inverse operation of differentiation. So we're going to start by finding a power series for f of x equals inverse tangent of 2x using substitution and integration. So we also did something very similar to this in section 10.9. So we can start by the fact that we know that if we take the derivative of inverse tangent of 2x, we get this function. So that's very helpful, because this will lead us to the idea that we started with this. So we can get our inverse tangent of 2x if we integrate 2 over 1 plus 4x squared dx. And that's the great thing about this, because we can create a Taylor series for this integration. And its integral will be the function that we're looking for. So that'll give us our Taylor series that we need. So the idea is we're going to integrate this function, which we can create into a Taylor series. And from that, that'll give us a power series for the function we're being asked to find. So let's start by integrating this. So we're going to have the integral of 2 over 1 plus 4x squared dx, and this is going to equal, if we think of this in terms of how we write a power series, if we write this as minus negative 4x squared in that way, we can then create, whoops, I already put my 2 out front, we can create our power series. So this is going to look like this. We have our 2, and then we're going to have our integral, and then our summation, and it's going to be our geometric series set up. And then our dx. And now we can integrate this. So we have 2 times the integral. We simplify this a little bit. We're going to have the summation. And now we have that negative. We can make that negative 1 to the n. We now have a 4 to the n. And now we have an x to the 2n. So when we integrate this, there's our constant. And then we're going to have 2 times the summation of negative 1 to the n, our 4 to the n, and our x is going to be to the 2n plus 1. And then we have to divide by our new power. So that means that our function, our tangent, inverse tangent of 2x plus c is going to equal c plus 2 times the summation of -1 to the n, 4 to the n, x to the 2n plus 1 over 2n plus 1. Now, this constant's got to be the same because they're the same function. Another thing to note here is the idea that at x equals 0, inverse tangent of 0 plus c has to equal 0, so that's what c is going to be. So you can look at it either way. So we're left with our series looking like this then. So now we just have our function. Inverse tangent of 2x is going to equal 2 times the summation of n equals 0 to infinity of -1 to the n, 4 to the n, x to the 2n plus 1, all over 2n plus 1. Now if you want to pull that 2 in there and simplify this a little bit so it looks like all cohesive and it looks like it goes together, what you can do is take this 2 that's out front times the 4 to the n and rewrite it this way. So you get 2 to the 2n plus 1. So when we rewrite the whole thing, it kind of goes together then. It's kind of cool how this works out. So we have our -1 to the n, and now we have 2 to the 2n plus 1. And then we have x to the 2n plus 1 all over 2n plus 1. So they all kind of go together. This is a much cleaner looking series than the previous one, but both are correct. Okay, so several times in your math history you should have heard about the binomial series, which is a way to write out any polynomial. So we're going to try to develop the binomial series from the idea that this is what you use the binomial series for. Anytime that you have a function in the form of 1 plus x to the k, we can write it out in this form. So 1 plus x to the k is the summation at n equals 0 to infinity of k, choose n items, x to the n. And when you write it out, you have 1 plus kx plus k times k minus 1 over 2 factorial x squared, etc. And the rate of convergence is 1. Well, this is really kind of a Maclaurin series, is what it is. So we're going to do it for 1 over x to the 4th, which is kind of cool because what we have here, if we rewrite it in this form, is we really are going to have a binomial series with k equal to -4. So we can write it out this way using what we have here. So we're going to have the summation of n equals 0 to infinity of -4 over n, -4, choose n items, x to the n. So when we write this out, we have 1 minus 4x, and then plus -4, and I'm writing this term now, times -5, which would be -4 minus 1, and then over 2 factorial times x squared, and then I'll write the third term too. So I'm going to have plus a -4, the -5, and then k minus 2 would be a -6 all over 3 factorial times x to the 3rd. So simplifying this, you would have 1 minus 4x plus 10x squared minus 20x x cubed. And then if you wanted to go on, you could, like that. So it's kind of cool how that connects something you learned in algebra to something we're learning in calculus. Okay, and then our final example is we want to approximate the integral from 0 to 1 of x cosine x to the third dx to 3 decimal places. So normally integrating something like this would be quite tedious, but what we can do is we can first find a power series and then integrate that, and that would be easy to approximate because it'll just be a polynomial. So we're going to let y equal x cosine x to the third. So we're going to start with the idea from what we learned before that we've worked with cosine x as a Maclaurin series. So we can just change it a little bit by using x to the third. So it looks something like this. It's -1. And now we're going to have, instead of x, we'll have x to the third to the 2n power over 2n factorial. Okay, so simplifying this, we have, this should have an n there, sorry, -1 to the n, x to the 6n over 2n factorial. Now we can combine that with multiplying it by x. So then we're going to have x times cosine x cubed. So we're just going to multiply our series by that x. And we're going to get 6n plus 1. So everything else will stay the same. We're just going to multiply x to the 6n times x, and it's just going to be x to the 6n plus 1. So now we're ready to integrate. Let's go ahead and do that now. So we're going to have the integral from 0 to 1 of our power series. Don't want to forget my summation. And this is just going to be a polynomial integration. So this is going to give me -1 to the n, x to the 6n plus 2, and now I have a 6n plus 2 in the denominator, times my 2n factorial. And again, I forgot my summation. Let me just squeeze it in here. And we're integrating this from 0 to 1. So when we do that, we have, substituting 1 in, for x, we have -1 to the n, 1 to the 6n plus 2 power would just be 1. And then the denominator is just going to be 6n plus 2 times 2n factorial. Minus, and when I put 0 in for x, I get 0. So I just get this constant. Okay, so now we were also to approximate it. So that's going to be part 3, is we're going to approximate. So we're going to use our alternating series estimation theorem. So what that is, in case you forget, because we haven't done that in a little bit, is the estimate is at most the absolute value of the first unused term Okay, so in this case we want 3 decimal places, so our first unused term will be the 4th term, because we want it to 3. So here's what we're going to have then. We're going to have our constant here. Write that down, that we got from part 2. So we want to write out the first 3 terms. Well, I'm actually going to write out the first 4 because I'm going to look at the 4th term to see how accurate I am. So I'm going to have 1/2 if I put 0 in, and then my next term is going to be 1 over 8 to the 2 factorial. And then my next term, when I put 2 in, I'll have a positive. And so I'll have 1 over 14 when I put 2 in. 6 times 2 plus 2 times 4 factorial. And then the term I'm going to use to check my accuracy, I'm going to have 1 over, this is the third, n is 3, so I have 20 times 6 factorial, and I'm good there. So simplifying these, I have 1/2 minus 1/16 plus 1 over 3/36. Those are the ones I'm going to use. And then, of course, the last term is going to be my accuracy term. So when I add these 3 together, I get an answer of approximately 0.44, doesn't look like a 4, 440. And if I check my accuracy, so if I take the absolute value of -1 over 14,400, this is equal to 1, 2, 3, 4, 7. So we have 4 decimal place accuracy. So this is accurate to 4 decimal places. So that's pretty accurate. That's a pretty good estimation. And this is probably the best example of how a Maclaurin or Taylor series can be used to do complicated functions, because our trig functions we saw, sine, cosine, and tangent, can be written very easily as a Maclaurin series, and then integrating it, even multiplying it by some algebraic expression, like in this case x, and we had an x cosine of x cubed, turned into a very simple power series. And then after integration, we had a constant, and then we could actually evaluate it, because it was a constant definite integral, so we could find the value. And we can see that it is a very accurate estimation of the real value. So that's the end of our discussion on Taylor and Maclaurin series. If you have any questions, you can feel free to contact me, and I'll answer them as best as I can.